Okay, in this lecture, we're going to have a look at the first technique for a supervised algorithm. So it's called supervised segmentation. Okay, to recall that in this class, we're going to focus on predictive models, yeah, whereby we want to estimate or we want to predict, okay, a target variable of interest. Okay, so what is supervised segmentation? It is basically segmenting. Okay, it is aimed at segmenting a population of data set, in order to to form subgroups that have different values for a target variable. All right. The condition is that when we form the subgroup, in each subgroup, the instances within that subgroup must have similar values for the target variable. Alright, so if let's say we have a classification case of a yes or no, or a male or female, we would expect that when we segment the population, we will have subgroups that contains one type of class in there, one type of label. Alright. Okay, this is an example, a simple example. Alright, a segment can describe, for example, middle-aged professionals who reside in London on average have a churn rate of 5%. Okay, so the definition of a segment, we can define the segment as being middle-aged professionals who reside in London, yeah, and then the predicted value, okay, is a churn rate of 5%, which will yield probably a yes or a no. So the question here is that what are the best segments? So the best segments would be the one that provides, okay, something that humans can understand. Okay, it's kind of difficult to interpret something when you don't understand the result or how it come to the result. Yeah, so here, okay, you want to be able to distinguish, okay, data points, right, to be a member of or to fall into one of the classes. If it's binary, okay, like in this case, a yes or no, that it is binary. Okay, but you can also have multi-classes. For example, you have high, low, and medium. Yeah. So we want to have the highest accuracy. Accuracy here refers to how correct the algorithm is predicting a certain instance. So we have the labeled data, we have the ground truth. Yeah, we want to see whether the algorithm is able to predict the target correctly. So the more targets, the more instances that an algorithm targets correctly, the higher the accuracy. Yeah. So how could we find the best segments? Well, one of the answers, one of the possibilities is to select informative attributes. There are other strategies, okay, but in this class, I'm exposing you to something called information gain, yeah, where it follows a concept of finding or using informative attributes. So how can we judge whether a variable contains information, good information or important information about the target variable? Right, that would be the question. How do we select informative attributes? Yeah. So here you're going to have multiple attributes. Commonly we have multiple attributes. So one of the ways is that, what I mean is that once we find out the most informative attributes, we can actually have a ranking of these attributes, because we can have an attribute that is giving the highest information, and then the next one is slightly lesser, and then lesser and lesser. Okay, so we can have a ranking of informative attributes. So a churn example here is: what variable gives us the most information about the future churn rate of a population? Okay, so these are the attributes here: professional, age, place of residence, income, number of complaints to customer service, amount of overage charges. Yeah, so here our job is to identify which of these attributes here listed is going to give us the most information gain. So what is this information gain? IG, yeah, not Instagram. Okay, IG is talking about how pure a child is than its parent. Okay, the purity here, how pure it is. So a parent is referring to the total population of data set that we have. Yeah. The child refers to the subset of the population after attributes have been applied. Okay, after we have segmented it based on a certain attribute. Yeah, we segment the population. Okay. So, in other words, a subset splits by each attribute with respect to a chosen target variable. Right? So, the aim is always to have a look at the prediction of the target variable, regardless of however that we segment the population. Okay, so here there's something called entropy, okay, which is referring to the purity measure, okay, that's used in IG. So IG basically measures how much an attribute improves entropy, okay, over the whole segmentation it creates. So when we're talking about improves here, we are specifically expecting the entropy to decrease and not increase. Okay, the lower the entropy, the better it is. Okay, so what is entropy? Entropy is a measure of disorder, okay, that can be applied to a set. Okay, so consider, let's say we have a set of properties of members of the set. So each member has one and only one property. Okay, so in supervised segmentation, the member properties will correspond to the values of the target variable. So this order here corresponds to how mixed, or impure the segment is with respect to these properties of interest. So so if, let's say, we have a segment, okay, and that segment has x and y instead of just xx, so this is less pure than this one. This is purer. Okay, so here I have given an example: a mixed up segment with lots of write-offs and lots of non-write-offs would have high entropy. So the more mixed it is, the more impure it is, the more entropy, and the larger is the entropy. So this is a formula for entropy. Okay, P is the probability, okay, of a certain property I within a set, okay, ranging from Pi equals to 1 when all members of the set have property I, and Pi equals to 0 when no members of the set have property I. Alright, so here the trick is to calculate the entropy so that we can know the information gain. Alright, so let's see a graphical view of impurity and entropy. So entropy has a scale of between 0 and 1. So 0 is more pure, it's the purest, it's just pure to the bones. Okay, and this one is completely impure. So all population starts off here, okay, being impure. As the properties or the attributes are applied to this population, you will receive, okay, subsets which is going to have a lower entropy. We expect it to have a lower entropy. Okay, if by applying a certain attribute, by segmenting the population based on a certain attribute A for example, and we don't see the entropy decreasing, then that is a clear indication that that attribute is just not informative. Okay, and the best case or the best scenario would be something like this, where you have a subgroup containing the same, okay, target variable here. Okay, so how do we calculate entropy? IG, okay, IG is a function of a parent and a child, okay, which is the population and the subgroup, yeah, where it is calculating the entropy of the parent, the purity level of a parent, minus the purity of the children, okay, the children for each and one of the subgroups that's formed from the parent when a particular attribute is used to segment the parent or the population. So an example here, let's recap the churn example from earlier. Okay, so we want to know if you can segment the set of people based on his or her bank account balance, okay, with either more or less than 50,000. The example here, where is it? Here, okay, so there's a few attributes here, yeah, professional, age, residence, income. So we want to know based on, okay, the account balance. Okay, so let's say this is our population, moons and stars. We have 16 moons and 14 stars, yeah. So when we calculate this so-called probability, yeah, of the moons, we get 0.53, of the stars we get 0.47. so since we're segmenting it based on the account balance of, you know, with the threshold of 50,000, okay, less, so we have lesser than 50,000 the balance, and here the balance is greater than or equals to 50,000. Okay, so what we have here is we have these children, okay, where this child represents a group, okay, a subgroup of balance less than 50, and this one is balance greater than or equals to 50,000. So when we have, okay, this, so these children, for example, okay, for this child, when we segment the parent, we get one child having only one star and 12 moons, right? Okay, so here we can calculate, yeah, the probability here of the moon and the star of this child, and the moon and the stars, the probability of the moon and the stars of this child. Okay, So here, this is actually the moon, and the dot here represents the moon, and the asterisk here represents the star. Yeah, it's not a dot matrix, it is not a dot operator. Okay, the asterisk is not a multiplication, but I just use this because it's easier. I mean, I was just typing this. Okay, so let's calculate the purity, the entropy of the parent. Okay, this is based on the formula. We get 0.99, which is very impure, because as when you recall, the impurity is between 0 and 1. Okay, and then okay, we calculate the entropy of the first child, which is lesser than 50,000. Okay, and we get 0.39. For the other child, we get an entropy of 0.79. Okay, this is logic, because if we take a look at here, we have more of the moons and only one of the star. So of course this one is expectedly that this child is of a higher purity than this child. So that's why its purity is 0.39. Okay, and this one, the second one, is 0.79. Okay, so we now, once we have the entropy calculation, we can calculate the IG, the information gain. Yeah, and here we have 0.37. Okay, by just having one attribute to segment a population, our population, we can't do a comparison. So logically we use another attribute to segment the population, and thus we can actually compare which of this attribute is better at segmenting the population. So for the second attribute of choice would be the residence. Yeah, and there are three values instead of two. Just now was more than 50 and lesser than 50, so we have this instead for residence. Okay, the values will be whether the person, the instance, owns the residence or rents it, or others, or just kind of like, staying with your parents, for example. So let's say when we apply or we segment our population using residence, we have these three subgroups or child. Yeah, and again we need to calculate the entropy. Okay, we have the entropy of the parent, which is very impure, and then we calculate the entropy for the residence equals to own, and the residence equals to rent, and the residence equals to other. Okay, and we get an information gain of 0.13. So when we compare residence, the IG for, if we use residence to segment our population, contrast with balance, we can see that balance attribute gives or yields higher IG, 0.37, and therefore we should use balance as the attribute to segment, or we can actually rank balance being the first and the second will be residence, and so on and so forth for the rest of the attributes. Okay, so the good thing about calculating information gain is that we have real proof. Okay, real proof of which attribute is of higher information gain. If not, it's just based on intuition. So again, predictive modeling or predictive analytics in data science is not based on hunches or crystal balls. We based on proofs, and this is known as the area of feature selection. Okay, so there's another one called gain ratio. Okay, and once again index something. Okay, I basically use a lot of IG. Yeah. Okay, so supervised segmentation is quite useful to produce a tree structured model. Okay, so usually we will put at the root the most informative attribute. Okay, and so this is the root. Okay, call it the root, and the branches or the leaves here are the target variable or the outcome. Yeah, so if let's say the next one, okay, will be less informative, attributes that are lesser and lesser informative. So with this we can easily explain, right? Can easily explain that if the person is employed, then the prediction is that this person is not going to write off. But if the person is not employed, and his or her account balance is less than 50k, so this person is most of the time is not going to write off. Okay, they're good people. So if let's say in contrast the account balance is greater than or equals to 50k, well, it depends on the age. Then if the age is less than 45, not likely to write off. But if the age is greater or equals to 45, then the person is going to write off. So this is just a hypothetical case to show the tree structure model that we can derive from supervised segmentation. So trees are also very good at rules, creating rules. So you can deploy your model, and there are rules, okay, that you can actually use in handling this write-off prediction or this write-off cases. So you can have like this example, if balance is less than 50 and the age is less than 50, then these people, this group of people, of loan applicants, for example, let's say, yeah, they should be careful with these people, okay, because they are more likely to write off. So what a bank can actually do is to sift through individual cases, have a close investigation of the background of these people within this group, as compared to people that falls under the rest of the other groups. They can relax the rules a little bit, okay, but with this one they have to be very careful. They have to be on their toes most of the time. Okay, so there's something called probability estimation, right? So here, instead of predicting if a customer is going to write off or not, it is more informative to know the probability that he or she will or otherwise. Okay, because if you're just saying write off or not write off, it's just like two big groups. But once we know the probability, then it's going to give you better insight into the instances or the data point in these two groups, subgroups. So frequency, this is frequency based estimate of a class membership probability. This is the formula. Okay, the probability of class C, okay, equals to n, okay, divide by n plus m, n where n is the number of examples in the leaf and m is the number of examples not belonging to the class C. Okay, so let's say we have something like this. Okay, we put it into a grid. We put it into a grid where we have here at the x-axis the balance and the y-axis is the age. Yeah. So the plus is are the people who are not going to write off, but the circles are the people who would write off. Okay, we can actually put it into a grid like this. Okay, and if we have a new applicant, we can see whether this person will fall into any of this grid. Yeah. So if we were to calculate the probability, yeah, okay, so we have the balance and the age, right? And here we have the leaf nodes, the outcomes. So if we were to calculate the probability of write-off of this group, okay, of people, so balance grade lesser than 50 and the age is less than 50, it's like young people. Yeah, so we get some 100% probability of these people writing off. Okay, and if we take a look at the extreme, okay, the extreme, which is this side, okay, of very wealthy and old people, yeah, which is this group here, we see that the probability of not writing off is also 100%. Okay, however, for this one we have only 10, okay, members in there, whereas this one is 12. So there is a problem with the frequency based estimate of class membership probability. So it is overly optimistic, okay, and therefore we should it can actually cause overfitting. So it's so if a leaf or a segment has only one positive instance, hence the estimated probability is 1, which is 100%. How confident are we to say that any data point that falls into that segment will have the class that this one instance happens to have, which is positive, since the evidence is very less as compared to a leaf segment with 100% positive instances? Okay, so the answer here is, or the remedy is, a Laplace correction. Okay, so Laplace aims to smooth out the frequency-based estimate of membership probability. Okay, the difference would be here. Okay, compared to the frequency-based, yeah. So it smoothes its estimate down from 1 to 0.75 to reflect uncertainty. This, yeah. However, as the number of instances increases, Laplace correction converges to the frequency-based estimate. Right? And well, that's how it goes. Okay, so if let's say we apply, okay, the Laplace, here we have, okay, once again, this is the part that is different. So instead of these two groups having 100% probability, we see that the probability now differs. So this one is 93% and this one is 92%. So this is better because of the evidence or the data point of this group is 12. So you have higher confidence that this probability that they are going to write off. So it is reflected here in this probability, which is 93%, as compared to this one, which has only 10. Okay, just only 10, and therefore our confidence should be reflected here with only 92%. Alright, so this is once we have applied the Laplace. Okay, so in other words, we are calculating the probability value based on the size of the evidence. Okay, the more the size of the evidence, the more confident we are. Yeah, an extreme, and maybe another example would be if let's say over here we have only 1 and thus over 1, and this one we have 10, this over 10, for example. Yeah, so we would have the same 100%, but this one should be actually of higher confidence, yeah, because the evidence size is larger than this one, and therefore the probability here should reflect that confidence, which is the evidence size. Okay, so that's why when we use Laplace, this is going to be reflected. Alright, so this covers for supervised segmentation. Alright, and you will learn other techniques in other videos. Till then, thank you.